Hello everyone, I am your trainer from Robbie Group Telnet. This course is about LTE frame structure. This will include the introduction of LTE and how an LTE frame is made. This video will cover both TDD and FDD frame. LTE frame structure is one of the topic in the LTE fundamentals that will be covered in day 1 of LTE radio network optimization training. In the day 2, we'll be covering LT KPS, LT drive test, day 3 LT features, and in day 4 we will be covering LT radio parameters. So let us start with the first topic of the day 1 training. Before we go into details of LT frame structure, let us have a look at LT worldwide deployment. As you can see that in the green area, most of the countries are already having LT network commercially deployed. Few countries which are marked orange or light green are still using GSM or 3G network. Let us have a quick comparison between WCDMA and LTE network. If you can see from the figure, in WCDMA network we have more number of network elements. For instance, we have RNC in WCDMA, while in LTE we don't have RNC, and that functionality is moved to E node B. So first thing is that less number of nodes, and all the processing done by RNC is now similar processing is done by E node base itself. If we have a comparison, then in LTE the network is very simplified. The latency is reduced as compared to WCDMA. What does it mean is that since in LTE we have less number of network elements, so the processing latency is reduced. Also, the latency is reduced on the radio part that we'll be discussing in the upcoming slides. LTE provides high data rates, high spectrum efficient, and flexible bandwidth. Here you can see that the throughput which was previously provided by UMTS network was a maximum of 40 Mbps, while in LTE network the throughput is more than 100 Mbps. With the increased number of smartphones all around the world, there is a high demand of throughput, which the previously deployed technologies were unable to meet, and LTE can meet that throughput requirement. In this slide, you can see different releases of LTE. LTE was first commercially launched in 2009, and the first release of LTE was R8, which was having basic features of LTE radio network, and which contained how the LTE frame structure would be, what would be the features that LTE will have, what would be the MIMO and the modulations and other information. With the passage of time, the LTE network is advanced into LTE Advanced, and the last release is R13, which is the LTE Advanced Pro, which has actually better radio network features, and which supports high modulation and enhanced MIMO. Here in this figure you can see different interfaces of LTE radio network. At the radio side, the UE is connected with E node B through UU interface. The E node B is connected with the serving gateway as well as the MME through S1 interface, which is further split into S1U and S1 MME interface. The serving gateway is having connection with the packet gateway through S5 or S8 interface, and the packet gateway is connected to the ISP service provider through SGI interface. Also, it has also having a connection with PCRF through GX interface, and the PCRF is having connection with the internet service provider through RX interface. The MME also connect with HSS through S6A interface. Now, these interfaces are divided into control plane interface or user plane interface. Control plane interfaces are those interfaces that actually carries signaling messages, and the user plane interfaces are those interfaces which carries user information or traffic information. For instance, the when a web page or a YouTube video is requested by the UE, it comes through the ISP service provider, which is the internet service provider, through SGI interface. This interface carries user traffic to the external network and from the external network to the internal LTE network. Then from packet gateway, this information is transferred to serving gateway. This is also a user plane interface that carries the information between the PGW and the serving gateway. Then this information is provided to the eNode B so that the eNode B can send it to the UE over the radio interface through S1U interface, and the eNode B will be using the UU interface. This is actually the explanation of how a web page or a video streaming is done by the UE and what interfaces it uses. The remaining interfaces, which are the control plane interfaces, are used for signaling messages for different functions. For example, for authentication, for policing, for other things, these interfaces are used. In this slide, we'll talk about FDMA and TDMA. Previously, in FDMA, when you have an available bandwidth, for instance 5 megahertz or 10 megahertz, in this technique, that bandwidth is divided into sub-bands or channels. Now, each user is allocated one sub-channel. When one user is using this sub-channel, the other user cannot use this sub-channel. So this sub-channel is dedicated to a single user over the entire time. This is not an efficient way to use your frequency spectrum. In TDMA, what happens is that you have your frequency bandwidth. Now, this frequency bandwidth is not splitted. The whole bandwidth is provided to a single user for a particular time so that it can use it to send or receive information. Then on the other time, the second user use it, and then multiple users can use the available bandwidth in different times. This is also not an efficient way that you can efficiently use your available spectrum or bandwidth. Because in TDMA and FDMA you cannot accommodate higher number of users on your available bandwidth. In OFDMA, this is actually a technique that is used in LTE radio access network. In this technique, what happens is that each user allocated a different resource which can vary in time and frequency. So here we're using FDMA and TDMA together. And why it is called OFDMA because the subcarriers are orthogonal to each other so that they cannot interfere because the spacing between the subcarriers is very less. Because the frequency spacing is less, so there is a chance that there would be interference between the subcarriers. To counter this, orthogonal frequency division multiple access technique is used that we will discuss in the next slide. If you compare this technique with the previous techniques, you can see that this technique is more spectral efficient. How? Because more number of users can be accommodated in the frequency domain and time domain split. Let us further discuss. In this slide, you can see that you have a known orthogonal set of frequencies, that is f1, f2 and f3. Now as you can see that this point is the center frequency of f1. At this center frequency you can see an overlapping of the sideband of f2. Similarly, you can see an overlapping of the sideband of f1 and f3 at the center frequency of f2, and same is the case of f3. Since there is an overlapping, that is why there would be more noise and the other frequencies are interfering f1, and similar is the case of f2, f3 and so on. Now these set of frequencies are non-orthogonal to each other. What we mean by orthogonal? This is the orthogonality between f1, f2 and f3. The orthogonality is achieved in a way that no interference at center frequencies from adjacent subcarriers sideband. F1 is a subcarrier, F2 is a subcarrier and F3 is a subcarrier. In the three subcarriers, when you can see is at the center frequency, there is no interference from the adjacent subcarrier sideband. So we have F3 here and the sideband is this one and this one. But it does not interfere with the center frequencies of F1 and F2. In this way, the orthogonality is maintained and the information is not interrupted by the other subcarriers. This is also a picture that represents the subcarrier transmitter operation and subcarrier receiver operation. In the transmitter operation, what happens is that we have subcarriers from F1 to F2 and up to Fn. These number of subcarriers depend on the available bandwidth that we have, because that available bandwidth is splitted into small subcarriers. Now we have our useful information here that we want to transfer. So some of the information will go to F through F1 and then to F2 and up then through Fn. At the receiver side, the same information is received and we have over received information over here. Now in this slide what you can see is that your user data is modulated. Modulation is actually used to represent your binary information into signal form. So the data is fed into the modulation block and you have your modulated signal here and up to here. Then inverse FFT will work. What inverse FFT will do is that it will combine these modulated signals to a single signal, and that information would be sent. Then similarly, FFTU operation will be done at the receiver side, and the one signal would be split into parallel streams of different signals. Then the demodulation will occur and we will have our information extracted. In this slide, we'll be talking about modulations that are used in LTE network. We have QPSK, 16-com, 64-com. Why we need modulation? We need modulation so that our information that is in terms of zeros and ones, that is in bits, can be converted into signal so that the signal can be transmitted. In QPSK, there is a change in the amplitude and the phase in order to represent different combinations of information. For instance, if the signal starts from here, we say the information is 0 0, and if the signal starts from here, then we say it's 0 1. If it starts from here, we say it's 1 0. If it starts from here, we say it's 1 1. Now in 16-com, what happens is that there is more number of points, so there is more change in the phase and amplitude in order to present information. These points get closer to each other in 64-com, so it means that there is a higher probability that this information which is using 64-com modulation will be deteriorated when there would be more noise in the radio network. So that's why if the user is very close to the site, there is less noise, then the user can easily use high modulation. When it goes far from the site, it can use 16-com. And when the radio conditions are not very good, it uses QPSK. Now the difference, one of the difference that the points are very close to each other in the constellation diagram. And secondly, you can see the 64-com, you can have 6 bits per symbol. In 16-com you can have 4 bits per symbol. In QPSK you can have 2 bits per symbol. This simply means that if you are using high modulation, you get more throughput because you can send more number of bits per symbol. If you are using 16-com, then your throughput will be further decreased, and if you are using QPSK, your throughput will be further decreased. Flexible channel bandwidth. In LTE network, we have a flexible channel bandwidth. What does that mean? If you compare LTE with 3G network, in 3G we have a single carrier of 5 MHz. If you have 10 MHz, you can have two carriers. But what if you have only 3 MHz? You cannot have a 3G network. You need to buy license and you have to pay license fee. So that is also a spending. With the passage of time, if for instance I have 10 MHz for my 2G network and I don't have too much voice traffic, so my bandwidth is actually not utilized or not efficiently utilized. What I can do that I can carve from that 10 megahertz, 3 megahertz or 5 megahertz LT carrier, and I can use the remaining 5 megahertz for my 2G network. So this is how LT flexible channel bandwidth helps operators to use their existing allocated band to launch an LT network. In LT you can have 1.4 megahertz carrier, which is of the smallest bandwidth that can be allocated to LTE network. Then we have 3 megahertz, 5 megahertz, 10 megahertz up to 20 megahertz. Here in this slide you can see bandwidth, number of resource blocks, number of occupied subcarriers, IFFT or FFT size, and subcarrier spacing. In LTE, if you can see here, all the information is 15. What does it mean? That the subcarrier spacing is 15 kilohertz. So in LTE, you have a subcarrier of 15 kilohertz. Now, if when the bandwidth increase from 1.4 megahertz to 20 megahertz, the number of resource blocks is also increasing. Also, the number of occupied subcarriers is increasing, and so the AFFT or FFT size. What does it mean? It means if you have 20 megahertz, you can have 100 resource blocks, and number of occupied subcarriers is 1200. This is actually calculated in a very simple way. For instance, you have 20 megahertz, you change it to kilohertz. So for instance, you have 20,000 kilohertz. You just divide it by 15, you will get a number that would be greater than 1200. But what you need to do is that you also need a guard band between your LT band so that it won't interrupt or it won't get interfered from adjacent frequencies. So the usable number of subcarriers that we have is 1200. In each resource block, actually, there are 12 subcarriers. So this is simple mathematics that in 1200 subcarriers you can have 100 resource block. In the next slide, we will talk about resource block in detail. Here you can see that there are not only the LTE bandwidth is flexible, but also LTE supports different bands. For instance, there are many bands for uplink and downlink for the FTD, and there are many bands for TDD network. These bands supports different channel bandwidth, so this is as per standard. Mostly we have LTE networks on, let's say, 1800. So in 1800 you will be having band 3. If you have that LTE network on your 800 band, then you will have band 5. And if you don't have an FTD network, you have a TDD network. Then in TDD network, what will happen that you can have a band 38, 39, 40, and so on. And with time and with new releases, the 3GPP is including more bands to support LTE network. In LTE frame structure, in the time domain, you have a frame of 10 milliseconds. In each frame, you have 10 subframes. So one subframe duration is 1 millisecond. In each subframe, there are two slots. So the slot duration is 0.5 millisecond. Then that slot is further subdivided into 7 OFDM symbols. Here, the figure shows the frequency domain representation of LTE frame. As discussed previously, the LTE bandwidth is divided into subcarriers. Each subcarrier is having a bandwidth of 15 kilohertz. When the 12 subcarriers combine together for a duration of 0.5 millisecond, that is 7 of DMA symbols, it forms one resource block. As discussed in the previous slide, this slide, you can see that if you have a channel bandwidth of 20 megahertz, you can have 100 resource blocks. Here we have a TD-LT frame structure. Before going to TD-LT frame structure, the main difference between maybe most of you already know that the main difference between TDD and FDD is simply that in FDD we have different frequencies for uplink and downlink, and TDD we have only one frequency and that is used for uplink and downlink in different times. For instance, in this frame, we have divided different subframes for downlink and different subframes for uplink. For instance, subframe number 0, 4, and 5 and 9 are used for downlink, whereas 2, 3, 7, and 8 are used for uplink. This subframe number 1 is actually a special subframe. The special subframes are actually used for downlink to uplink switching. Here you can see the example of different combinations that we can have in TDLT. The different combination is simply that you can have either more number of time resources allocated for uplink or more number of time resources allocated for downlink in case of combination 5. Now in case of combination 5, if your downlink requirement is too much, then you can go for this option. Otherwise, you can also have a balance between uplink and downlink. For instance, in the combination 1, you have 4 subframes for uplink and 4 subframes for downlink. So the uplink and downlink ratio is equal. The special subframe consists of downlink pilot time slot, uplink pilot time slot, and guard period between them. So here you can see the timing at the E node B. This is for the downlink pilot time slot, and this portion is for uplink pilot time slot, and this is the guard period. And this is the timing at the UE side. The guard period is actually used so that no overlapping occurs between the downlink and the uplink. Otherwise, our information that would be retrieved would be interfered. In this picture, you can see the scheduling in downlink in LTE. As you can see here that different resources are allocated to user 1 in the frequency domain and the time domain. And these resources are allocated dynamically. So any resources where the user 1 experience the best quality can be allocated to user 1, and similarly the resources of time and frequency domain can be allocated to user 2 and user 3 and up to so on. Here you can see that if we have more users in LTE, then few number of radio frequency and time resources would be allocated to user 1, and the rest would be divided into other users. Then we will be experiencing low throughput, but if there are less number of users, then the throughput would be high. But the best thing is that wherever the user 1 or user 2 experience the best quality, that resource is allocated to that user. Now, if we further discuss about this scheduling, we can say that dynamic channel dependent scheduling allocates a number of these time and frequency resources to different users at different times. In that way, it is possible to schedule users on the frequencies they experience the best quality on a certain time interval. The transmission time interval of LTE is very short, and that is 1 millisecond. Scheduling in uplink is done by SCFDMA. In SCFDMA, you can see that frequency and time resources are allocated to a single users which are closer to each other, and they are not distributed throughout the whole bandwidth. The benefit of this is to have a low peak to average power ratio. What we'll get if we have a low peak to average power ratio is that the battery will not drain quickly, and there would be less requirement of power by the UE to form the signal to be sent to uplink. So in uplink we have SCFDMA, and in downlink we have OFDMA in LTE. Here you can see the LTE radio interface between the E node B and the UE. The first layer that we have is the physical layer, then we have the MAC layer, then radio link control and PDCP layer. At the physical layer we have the physical channels, then between the MAC layer and the physical layer we have the transport channels, between the radio link layer and MAC layer we have the logical channels, and between the PDCP and radio link control layer we have the EU-TRAN radio bearers, and above PDCP we have the EPS bearer. So what is the functionality of the physical layer? Antenna and resource mapping is done at the E node B side. Modulation and coding is also performed at the physical layer. At the UE side, antenna and resource demapping is performed. Demodulation and decoding is also performed. At the MAC layer, at E node B side, the MAC layer performs the HARC and ARC as well as the MAC multiplexing function. Whereas at the UE side, the hybrid ARC and MAC demultiplexing is performed. The radio link control layer, what is that it concatenate, also segmentation is performed, and also ARC is performed. At the UE side, what happens is that ARC and decoding is performed. At the PDCP layer, what happens is that the header compression and ciphering is performed, while at the UE side the header decompression and ciphering is performed. Here you can see, as we discussed earlier, that in LTE network we don't have the RNC, and the RNC functionality is actually done or is managed by the E node B itself. So inter-cell radio resource management is done by the E node B. Also radio barrier control is done by the E node B. The connection mobility control is also done by the E node B. Radio admission control, management control, cell configuration, dynamics, resource allocation, all is done by the E node B itself. Previously, the functionalities like intercell RRM, radio source management, connection mobility control, radio admission control, all these are the configuration of the RNC. Now the E node B is also having the functionality to perform handovers using the X2 interface. That is why the X2 interface is very important between the E node Bs, so that the E node Bs can communicate directly to each other. At first, if the X2 interface is established and configured between the two E-node Bs. Then when a UE moves from the coverage area of one E-node B to the other E-node B, the handover is usually performed by X2 interface, that is called the X2 interface handover. And when the X2 interface is not available, then S1 interface is used for the handover between the two E-node Bs. LT bearers. The EPS radio bearer service describes the overall connection between the UE and the core network edge node, which is the PGW. EPS carries the end-to-end service and is associated with quality of service attributes as decided by the operator. User data is mapped on the radio bearer from the UE to the eNode B, and S1 transport bearer between the eNode B and serving gateway in core network. Between serving gateway and PGW, a S5 S8 bearer is used to carry the transport between the nodes. Also, there is an external bearer that is between the PGW and the ISP provider. Similarly, there is a bearer that is called the APS bearer service between the UE and PGW as already discussed, and also there is the end-to-end service between the UE and the ISP service provider. EU10 radio bearers is between the UE and eNode B, and the access bearer is between the eNode B and the serving gateway or packet gateway. Here we have the radio interface, and between the eNode B and the SGW or PGW we have the S1 interface, and we have the GI interface between the PGW and the peer entity, that is the ISP. Thanks for your learning, and see your next topic, which is LT channels.